And welcome once again to the Convex stream. So today we're going to be talking about possibly one of the most important topics, which is network security. So all topics of security that are relevant to the Convex network and digital assets, how we protect smart contracts,
all topics of security that are relevant to the Convex
how we basically
network,
make sure that
digital
everything
assets,
works in a fully
how we
secure
protect
smart
so
contracts,
all topics of security that are relevant to the Convex
how we basically
network,
make sure that
digital assets,
some of
how we
the
protect
smart
so
contracts,
all topics of security that are relevant to the Convex
how we basically
network,
make sure
digital assets, how we
protect
protect
smart
so
contracts,
all topics of security that are relevant to the Convex
how we
network,
basically
digital assets, how we protect so
contracts,
all topics of security that are relevant to the Convex
how we
network, digital assets, how we protect so
any questions you want to ask at any point, and I will just keep an eye on the chat and answer questions as and when they come up. So, network security. So, big topic. I just wanted to start out by making an important distinction. Yes, thanks. There was a bit of an echo. I had a YouTube open in the background, so I've just killed that now. So hopefully that's okay. What I'd like to distinguish is first of all, you've got the security of the client, the user of the network, and that's the security about your own assets, your own transactions, all of the things that you do on the network itself as a user or as a business or as an individual. Then you've got the security which relates to being a peer operator. So if you're someone who's going to run and operate a peer on the network, that has its own set of security concerns, which are a little bit different from the concerns you might have if you were a regular user. So not every user of the Convex network is likely to run a peer. In fact, probably only a relatively small number of people will run peers. So that's a much more specialized kind of role in the ecosystem. And then the third area, which is of course important and sort of ties it together, is okay. Well, how does the security for the network as a whole operate, and how do we make sure that even if the individual bits are secure, how do we make sure the whole thing operates in a robust and reliable way? And of course, this is a particularly challenging environment and topic. I mean, we're talking about a decentralized network. So this isn't simply, securing some app on your own computer. This is a network which is open to the public, and anyone can join, and anyone can participate. And in some ways, that's the great power of decentralized systems, that you do have this level of openness and the ability for everyone to participate. But it also presents a lot of security challenges, and I guess that's what the call about is today. Is talk about some of those. Talk about what we do in Convex. How we approach some of the challenges of security, and any other topics related to security that are of interest. So feel free to fire in questions at any time. One other thing I'd say is security is a deeply multifaceted topic. It's not just one thing, and in fact, there's it's a layered thing. There's many different things to think about in security. They all kind of need to fit together, and there's also always trade-offs in security. So you're always facing a trade-off, and the ultimate secure system is a system that nobody can use. Yeah, the more usability you want, the more you have to loosen the security requirements. So some of this is about thinking about some of these trade-offs, and how do we make the right trade-offs between ease of use and absolute security. And there aren't necessarily hard and fast right answers, but I think there's a lot of principles which we can apply, which are powerful and help the whole ecosystem to be effective and to do what it's supposed to do. I will caveat that I do have a little bit of a background in cryptography and building decentralized systems, but I don't class myself as a security expert. So some of the things, I don't claim to know everything about this field, and I'm always keen to learn. So if people have ideas or improvements in the way that we do things, then very happy to have any of those kind of discussions as well. Either drop things in the chat if there's something interesting people want to talk about, or we can of course discuss on the Convex Discord. And we're in the stage right now where we're about to launch ProtoNet, which will be the first live running version of Convex with real assets. and what and what we have for the security version in the initial thing is hopefully is going to be what we then continues for the mainnet and future versions of Convex. But we are still in development. Think of it a bit of like an open beta that everyone can participate in, and there are still room to make enhancements and improvements. So it's very much very much welcome any sort of suggestions on things that we can do better on any of these topics. Okay, so I will kick off talking a bit about client security. So what security we need for clients and users of the network. So the most important thing here is that it's kind of an access control problem. Yep. In Convex, every single user gets an account on the network. You can have multiple accounts, but you have to have at least one account to use the network. And this account is sort of like the entity which defines the security boundary for a user. Yeah. So whenever you do anything on the Convex network, that's kind of your entry point. Yeah. So as far as the network is concerned, I might be account number 111. Yeah. And any transactions I send that affect what I want to do with that account, they're all targeted at this account 111. And other people, of course, have their own different accounts. Now the accounts can store information. Yeah, they've got their own little data storage. They can store, or they can store, or they can control. Perhaps is a more precise way to say it. They can control digital assets. So if account number 111 has a bunch of NFTs, then account number 11, you want it to have the right to transfer those NFTs and to do other things with the NFTs that it controls. But at the same time, of course, you don't want account number 200, which might be my worst enemy. You don't want him to be able to do anything to the NFTs. You need the access control to be restricted to which accounts have the ability to control a particular asset or a particular entity on the network. And it's not just assets; it includes things like governance. So if you're a member of a voting committee, voting on a new proposal to upgrade the capabilities of an auction house, for example, then those votes also need to be access controlled and authorized. And the way we do that on Convex is via accounts. So whenever you start a transaction in Convex, you're always saying what account is that transaction going to be. We call this the origin account, which is, I think, the same terminology that's used in Ethereum and a couple of other decentralized systems. But this is the account that was the source of the original transaction. Now, how do we make sure that only the right transactions get executed? We're basically using digital signatures. And digital signature system we use is called ED25519. It's an exceptionally good digital signature scheme. It's fast. It's sort of computationally efficient. It's very secure. I don't believe there's any plausible threats against ED25519 security at the present day that anyone can foresee. It's used in banking, it's used in securing the internet, it's used in site certificates by big internet players. It's basically pretty much a gold standard as far as cryptography is concerned. And what's a digital signature? So I think of it just like an unforgeable paper signature. You've got some kind of message, some kind of information that you want to convey, and you can put a digital signature basically on any sequence of bytes, on any message you want to sign. And the properties of this signature is other people can look at the signature. They can verify two things primarily. One, that the signature was from the person who claims to have signed it. So who was the person who created the signature. And the second is you can look at the message and the signature together, and you can say, was this the exact message that was signed? Yeah. So if someone changes the message and tries to use the same signature, it'll come as invalid. Yeah. So the signature provides that sort of a way of saying this is the information which I've attested to, and I'm saying this is the message I want to send, and I've signed it. So no one else can create a different message with your signature. Yeah, they can see the message that you've signed, but they can't create their own message and then create a signature which means that it looks like you signed it. Now the important thing about this, of course, is that when you send the transaction to the network, what the network is doing is saying, okay, I've just received this transaction. This transaction has a signature. It's for account number 111, which might be my account, and it will check, well, is this signature correct according to the key that I have on record for account 111, and if that signature is correct and it matches the key that's connected to the account, then that transaction gets executed. And if that signature is wrong, then the transaction is going to get rejected. And what's important about this is, of course, is that only the transactions that you as a user authorize actually happen on the network. Yeah, there's no way that you can get a transaction past the signature validation step as transactions are executed. And that's what provides you security. Yeah, so as long as you keep your private keys secure, and you are the only person who can sign transactions for your account, then no one else can touch your account. No one else can touch any digital assets that are controlled by that account, and no one else can take any actions that you don't authorize, if you like, with respect to that account. And that's fairly standard. That's broadly how blockchain networks do security on transactions. There's a couple of different variants, but basically it's the same thing. Yeah, the digital signature is what proves your right to execute a transaction on that account, or if it's a case of some kind of UTXO kind of based system, your ability to spend the outputs of a previous transaction, which would be like what happens in Bitcoin. So it's a very well proven and very strong method, with a couple of caveats, and probably the most important caveat is, well, in order to create these signatures, you need to have a key. You need to have a private key, and that you need to keep that key secure, because if anyone else gets hold of that key, then they'll be able to sign things on your behalf, and then of course as soon as they can do that, they can create their own transactions, they can take control of your account, they can help themselves to any assets, they can vote on your behalf in any elections. So all the bad things that you want to stop people from doing suddenly become possible if your private key gets leaked. So from a user perspective, the most important thing is the security of that private key, and making sure that is kept securely, and no one else, and particularly not any malicious actors, ever have a chance to get their hands on it. So how do we do that? I think most importantly, these are private keys that should never be sent anywhere. They should never be given to anyone else. Yeah. So it's something that you want to keep on your device. If you're using something like a hot wallet or a warm wallet, and also that if you want to keep a very secure key, like for holding a treasury or some more significant assets, you don't want to keep it on a device at all. You want to keep it in some air-gapped system where it's not actually connected to the internet anywhere. And then if you have to do any signatures, it's an extra step, because you're going to have to go to that machine and make a signature in a sort of in an isolated environment, and then come back with the signed transaction in order to transmit it. But that's an extra layer of security if you really need to make sure that that's very well protected. So the security of the private keys, you can take the keys and you can, if you like, put them on a metal plate and lock them in a safe, or you can split them into sub pieces and distribute them among trusted people. There's a lot of very sophisticated ways you can try and protect these sort of highly valuable keys. But for the average user, that's probably overkill. For the average user, you actually want to use your key. Yeah, you don't want to be going and calling up people and opening safes and flying to Switzerland in order to use your account. So typically, you would want to keep that key on your device, securely kept on your device, so that you can use it when you need to. And we'll talk a bit more about exactly how we do that. But that's the model that the typical user would be using. So great question. Assuming the private key is leaked, Convex has a way to change the private key. Isn't that true? So yes. So each key is really a key pair. You've got two parts of the key. You've got the public key and the private key. Now the public key is public. You're quite happy to give that to people. You can say, this is my public key, and people can't sign anything using the public key. All it is really is an identifier that proves that you used your private key. Yeah, people verify by using the public key. And the public key is actually what's stored on the network against each account, so that when it verifies a transaction, it'll check, well, does that signature verify for that public key? And that public key is really what's used to test the signature. Is this the signature that, is this Mike's signature or not? Yeah. Now, Convex does have a method whereby you can change that public key. Yeah. So if your account number 300 and you have a public key and you're a bit worried that you lost your private key. You don't know, but you're a bit worried. You might have leaked it, you might have done something stupid, you might have sent it in an email to someone, you asked them to delete it and they said they did, but someone maybe got a copy somewhere, maybe it's sitting on a mail server. You're going, okay, this is not a very comfortable situation if there's some real assets in this account. So, well, one thing you can do is you can just move all the assets out of the account and drain it yourself so that it's not worth attacking. But the other method you do is say, okay, I'm going to assume that key is compromised. I'm going to assume I've lost control of that key. So what I'm just going to do is I'm going to create a new private key and a new public key, and I'm just going to change the public key on the account, which I can do using my previous key, because I can still transact with it. Yeah, it's still there, and I can change the public key to a new public key which corresponds to my new private key, and the old key is now useless. Yeah, that won't work anymore with the account. So I'm safe if I've done this correctly. Yeah, even if someone has got my private key or my old private key, it's now no use because I've changed the key associated with the account, and therefore an attacker can't do anything useful. And of course, when you do this, you just throw away the old key and you never use it again. Yeah, just assume that key is compromised. And that's not a problem. Generating keys is cheap, it's easy to do, you can create thousands of them if you want, and there's also effectively, I mean, it's not quite infinite, but there's effectively infinite supply of them. You can mint keys forever and you're never going to run into any problems. So yes, so that's key rotation. You can rotate your key pair as a user to protect your account if at any point you're worried that your private key is being compromised. I would add the caveat that if someone steals your private key and they act before you do, they can change the account to their new private key, yeah, and hijack your account, and then you're locked out. Yeah, so this is why the private key security is so important. If you lose control of your account, someone can then just change the public key on that account, and they now effectively own that account. There's nothing you can do to get that back because you've not got their private key, and the old private key that you used to use is no good anymore. Yeah, so yes, you can rotate keys, and as long as you keep your own private key secure, you're fine. If you lose your private key or you're worried you've lost your private key, then rotate it, throw away the old private key and use a new private key as soon as you possibly can, because as long as you do that before the attacker does, you've restored the integrity and the security of your account. Yeah. Now there's an interesting question about should tools like wallets or mobile apps do that for users automatically on some irregular occasions? And the answer to that, well, maybe they should. Maybe some tools it makes sense to automatically cycle the keys for users, you know, every day or something like that. Now that's got pros and cons. It's got pros that if an old key gets lost, then you know it's not a problem. It's got cons in that you know it makes it harder to restore your key if you kept a backup of some old key and you've cycled it a few times and you now haven't got a valid backup of your latest key, that's going to be a problem. Now there are ways around that. You can use these things called deterministic wallets to create a series of keys, and then you can regenerate that entire series of keys, which is quite cool. But that's a little bit extra complexity. Yeah, so it's really a decision for the app and for users whether it makes sense to do rotation regularly. Couple more questions. What do keys look like? Keys look like a I'll show some actually. Keys basically are hex strings, or they're 256 bit or 32 bytes of data. They can be represented as hexadecimal strings, so 64 hexadecimal characters, you know, is 32 bytes, and that's for the private key. The private key is 32 bytes, and what we actually use is we use a thing called a seed. So the seed, which we use as a private key, is good because you can create the public key again. So you actually only need the private key, and then you can regenerate the public key as needed. So that's why we use what's called an ED25519 seed. That seed can be basically any 256-bit integer or any 32 bytes, and as long as you generate that randomly with a secure random number generator, no one else is going to be able to guess it. Yeah, you just need a good source of random numbers to create a big random number, and then use that as your seed, and you're good. So it's quite a simple process. Let me just show a couple actually, because I might as well jump into doing a quick bit of demo of some of the key stuff. I've just got a couple of command prompts here, you know, good old Windows PowerShell, and what I'm going to just do is use the Convex key command line interface just to show what I've got currently. So the way that this works is I have a bunch of keys in what's called a key store. So it stores multiple keys. If I say if I list my keys, well, it's got a key store password. Yeah. So if someone steals the file that is your key store, unless they've also got the key store password, they can't actually access the keys within the file. Yeah. So this is one of the multiple layers of security. Yeah. There's a password on the key store which has got your keys inside. So enter a password, and you see that basically there's 11 public keys in this key store, and there's actually a private key for each of them, but again, this is security. You don't want to show the private key, we're just showing the public keys, so you know these are the keys that I've got, and these are all hexadecimal numbers. And in fact, if you went and created an account on Convex, this is exactly the number that you would use to provide the public key onto a Convex account. Yeah. So it's basically a little key database that you can keep on your machine. So that's what the keys look like, and the private keys are similar. Yeah, they're just a hexadecimal number that you generally don't want to display to anyone, but it's the same kind of concept. Another question from Nicholas: if you lose your private key, then you wouldn't be able to sign the transaction to transfer the keys or change pair. Correct. That is correct. So, or at least it's correct in the basic case. Yeah. I'll add a couple of caveats to that. If you can't get into your account at all and you've got no way of getting in, yeah, you're stuck. You're not going to be able to get any funds out. You're not going to be able to move any transactions. That account is effectively dead from that point onwards. I would make a couple of caveats to that. One, if you lose your private key, you can still, if you've done it in the right way, you can have a way of regenerating that private key. Yeah. So depending on how you generated that private key in the first place, you might be able to recover it. Yeah. And I'll go into an example of this. Why don't we do an example? So we have a convex key generate command. Yeah. I can enter a key store password, and it's created a new key. That's the public key for the key, and I can give it an encryption password for the key itself. And okay, that's a new key. That should now be in my key store. Yeah, C7DF. Yeah. So that's a quick way of creating a key. There's also another way of creating a key which uses actually this is a standard from Bitcoin, which is quite a cool standard. So I do convex key generate, and I'm going to do BIP39 is the extra option. And if I do BIP39, again I need a key store password. What it's going to give me is this phrase, yeah, board, velvet, regret, weasel, artifact, panel, goddess, scale, lemon, public, cross, trick. Yeah, and that's a mnemonic phrase that can be used to regenerate your key. Yeah, so I can copy that, I can write it somewhere, I can store it in a safe, I can do what I like, whatever mechanism you want to keep that safe. And I also have a passphrase. So I'm going to enter a passphrase, which hopefully you want to remember or also store securely. And I'm going to just enter something random here. And that has also created a key, yeah, for me. And I can encrypt that. Now that key I could regenerate if I had both those words, those 12 words, and the passphrase that I used to generate the key. If I had both of those things, I could actually reproduce that key pair, so the private key and the public key. So that is a method you can use to have a backup of a key, is to generate it using this technique, and then you can always regenerate it using the mnemonic and the passphrase. Now, of course, there's the other risk that if you write this stuff down and your passphrase is guessable, or they can find the passphrase somehow, then this is as good as having the private key. Yeah. So your security needs to be just as good as for this as it would be for the private key itself. But it is a way that you can regenerate keys if you've completely lost them and you want to do it this way. So that's the first part of the answer, is there are ways of regenerating these keys, providing you've got some mechanism that enables you to do so. The second thing I would say is if you've completely lost access to accounts, so you've got no private keys, no public keys, there are a couple of ways that you can get access back, but only if you took action beforehand. So Convex has a notion of an account controller, which is like a backup mechanism for getting into an account. Yeah, so that backup mechanism for getting an account, that controller, if you set that controller to someone who you trust, who can then come in and restore your account, then you can get back in. But again, you're making a decision that I want to trust someone else, or I want to trust a smart contract or a DAO or some other system to have access to be able to recover my control of my account. So that's an option that's available. If people want to use that, they can set an account controller and have that as a recovery backup method. The final thing I would say is, well, even if you've lost control of the account and you haven't got a controller, if there is some mechanism by which, so depending on the assets, yeah, some assets may have their own recovery mechanism where they can be externally transferred. Now, a fully decentralized asset wouldn't have that capability, but if you had an asset that was like controlled by a central entity, like let's say a security token, and they were tracking shareholders, and they had ways of validating who the correct owners are, and they wanted to be able to fix transfers and stuff like that, then they could have that power, depending on the asset. So that's another option for recovery, but that is depending on the asset. What are the rules of that asset? Does that asset have rules that allows it to be controlled and accessed from elsewhere? But yeah, really great question. I mean, these are the important considerations, and exactly what I think app developers need to think about. What is the risk? What is the appropriate backup method that you might want to provide to people as a fallback in case something goes wrong? And obviously, losing a device, if you haven't kept a backup of keys, your keys are gone. So that's an important consideration for more valuable accounts. Lots of questions. This is great. Keep questions coming, by the way. I mean, it's great to know, great to sort of respond to these, and also know what people are interested in. Convex account abstraction can lead to reduce the risk of compromise or lost keys. Yeah, that's exactly what I just described. You can have an account controller, sort of an abstract controller who can then come in and recover your account. So that's part of what the account abstraction in Convex enables. Another good, interesting idea: if you change keys with every transaction, could you avoid being tracked? I mean, maybe. I mean, the transactions are visible, but the thing about changing a key is no one knows whose key it is. Yeah. So if you rotate keys on accounts, people can see that the key changed, but they don't know whether it's the same person or not. Yeah. So it does add a certain layer, let's say obfuscation, to what may have happened to an account and the ownership of the account. So I mean, it's visible. It's not. So I see someone saying it's like Tornado Cash. It's not like Tornado Cash. The transactions are visible, but the account is pretty pseudonymous. Yeah. Now, Tornado Cash actually hides the transactions. You don't know who sent to who, or who sent what to who. Yeah. Here you can see which account sent what and what they did, but you can't necessarily tell who owns those accounts. So that is kind of like Bitcoin or Ethereum in that respect. Is there anything encoded in the keys to help distinguish between testnet and proto-mainnet keys? Great question. There's nothing encoded in the keys that do that. I mean, I would say that one of the critical things is don't reuse test keys on if you've got some test keys, or you've got some low security keys that you're using for a hot wallet, don't reuse those for anything valuable. Yeah, but you can use the same keys on both if you really want to. Would I recommend it? Probably not. In fact, almost certainly not. So, but we don't actually enforce that. Yeah, you are allowed to use any ED25519 key. So buyer beware. What I would say is that it isn't such a big problem. It isn't just such a big problem because replay attacks aren't very likely. So replay attack is when you take something that's been signed on one network and then you play it back on another network. It's probably useless on Convex, or very unlikely to be a dangerous attack, because if the account number's changed, so you're going to get a different account number on different networks. If the account number's different, then you can't do a replay attack. So replay attacks are much less likely than they would be in something like if you reused a key in Bitcoin or Ethereum, because they don't have a separate account number. The replay attacks would be a bigger concern there. But yeah, good question. Should we put anything extra in to distinguish than that? Well, we could, but I think there's also downsides to that. Yeah, it's extra complexity, and the more things that you allow to go wrong, the more things often do go wrong. So it's a tough one. But yeah, I think we'd probably say, look, just new keys every time you do anything new would be the best approach. As I say, keys are cheap to create. Yeah, you can mint as many as you like independently. So you know, I would always create new keys whenever doing anything new. Would it be easier to use MetaMask? MetaMask is a front end. Yeah. So what MetaMask is doing is more or less this kind of thing under the hood. Yeah. It's keeping keys for you, and it's signing some transactions for you, and it's just managing some aspects of key management for you in hopefully a secure way, although it has had certain problems in the past. So there are many different ways of creating user interfaces that manage keys for people. The user doesn't actually really need to know about any of this in most regular usage. It's not necessary for them to know that this is going on. So in most graphical user interfaces, you're never going to see these keys or know what kind of key rotations happening. The only place where you really need to think about it is, well, what's the backup recovery mechanism for the user? Yeah. So if you want the user to be able to recover their account on a different device, well, how is that device going to get the key? Are you going to store it somewhere? Are you going to give them one of these sort of phrases so they can restore the key themselves? Are you going to have a recovery mechanism so that you can go in and give them a new key and restore control over the account as sort of like a separate service or something? So that's just a decision you have to make based on the app and your various threat models. Best practices of storing keys or passphrases so that hardware failure does not result in lost keys, and storing them online does not lend them vulnerable to leaks. Great question. So it depends a little bit on exactly how important these keys are. So I think what we do by default here is quite good. So if you generate a key like this, yeah, with a BIP39 key, and you've got like this mnemonic code that you can use to regenerate the key, and you do this on a secure machine. If you're paranoid, do it on a machine that's never been connected to the internet. If you're not so paranoid, you can do it on a machine that you just don't think has been hacked. And then enter a passphrase which is reasonably strong. And you've got your now key generated locally. It's in your key store. What would someone have to do to get into your key store? Well, they would need two things. They would need the key store file itself. So it's actually a file. It's a file on the. In your in your home direct, somewhere in your home directory. It's just a little PFX file, and that is encrypted. So not only would they need the file, they'd also need whatever passphrases you use to protect that file. So they would need to either guess your passphrase, or they would need to somehow intercept your passphrase. Now, in order to intercept your passphrase, they'd sort of need control of your machine anyway. So if you've been fully hacked and they control your machine anyway, and they can see everything you type, I mean, your keys are pretty much gone anyway at that point. So assuming they haven't managed to get that level of control over your system, then the key store alone is not enough for them to get your keys, assuming you've used good enough passphrases with a bit of entropy. These passphrases, they are pretty secure. I mean, the file format and the security is very good, but it is password-based encryption, so it's as good as you make your passphrases to some extent. And someone who's got enough processing power can try a lot of password combinations and try to guess it. So that's a risk. But yeah, you can then just use you can use physical media to store the mnemonic and optionally the passphrase, ideally separately, and then you've got a recovery mechanism if your device is lost, if your key store gets destroyed in some way. So you can always recover the key store, and then when you use the key store is always encrypted. Yeah, the only time that you actually it actually gets decrypted and the key is actually in an unencrypted format is when you use it. Yeah, so the hacker would somehow have to be able to intercept, either hack your machine completely or intercept all the stuff that you're doing and like look inside memory on your machine, which basically means they've got complete control of your machine anyway. So that would be I'd say good enough for most regular users kind of approach. So I see a question here: hardware wallets. Yeah, so you can use hardware wallets. So hardware wallets are devices that basically store keys, and they can do signatures, and the key never comes off the hardware device. Yeah, so even if your PC gets hacked, they can't do anything with the hardware wallet because there's no way to get the key off the device itself. Now that's good. It's extra security. It's also annoying. You have to have a hardware key, and you have to confirm signatures and stuff on the hardware key. So that's a extra security, a little less convenience is the trade-off with hardware keys. But yes, you can use a hardware key. As I say, we use a standard key signature algorithm, ED25519. So that's, I think, pretty standard on all these hardware keys. So that's definitely a possibility. Yeah, cold storage, so having a safe, putting recovery keys inside the safe if you need to restore it. The other thing you do is you can lock things behind multi-signature vaults, for example. So Convex is pretty flexible on this. If you wanted to create a vault where transacting on behalf of that vault would require multiple parties to approve a request. Yeah, so imagine like a little request. Yeah, I'd like to withdraw, $100,000. Yeah, and that request goes into a queue, and then multiple parties get to view that queue, and they have to vote yes or no to that request. And if anyone says no, then it gets vetoed, or it gets delayed while up for arbitration or something like that. So you could have one of these kind of multi-signature, multi-party validation schemes for high-value assets that you don't want to be immediately available, and then no private key would let anyone access the assets immediately. Yeah, they'd have to be able to control multiple keys held by multiple people, and do that, and there can be a time lock. Yeah, so you've got like a 24-hour window before withdrawal can be executed. So all of that kind of stuff is quite easy to do on Convex if you want to have those extra levels of security. That's probably the kind of stuff you'd do if you had some kind of high value treasury or a DAO or something like that, where you've got some significant assets being managed by some kind of smart contracts. But yeah, great question. Would crypto blinded transactions akin to Monero ever be feasible for Monero? But yeah, that means Convex. So that's an interesting question. We haven't implemented anything like that. I mean, so I think you'd say that Convex is closer to Bitcoin or Ethereum in the sense that it is a public network, and visible pseudonymous transactions is kind of how Convex works. Would it ever be feasible in the future? Well, maybe. Yeah, obviously that would be a sort of version 2 Convex kind of thing. And interesting question about, it's a double-edged sword. Yeah, I mean, some of these kind of things can be great for privacy, but dangerous for crime, and the lack of transparency is a problem. So the current balance we're striking is pseudonymous, and strong security but pseudonymous, quite high transparency, pseudonymous, but pseudonymous, yeah, to maintain people's at least if you want to be pseudonymous, you can be pseudonymous. Yeah, you can always say this is me, but you know, you don't have to. That's an option for users. So, but yes, in the future we might be able to do some more secret stuff, but it's going to be an extension to Convex if that is. And I think that I think we just have to be very careful with things that would facilitate very high levels of privacy can be misused. And you know, it's a complicated balance to get right, I think. So I think the research is still open on how best to handle that kind of thing. Great question. Couple of questions. How peers secures against attacks, and peers needs to have access to a private key. Yes, the peers need to have access to at least one private key. Yeah, which is the key that they use to sign their own interactions with the consensus protocol. We spent a lot of time talking about key security and user security. I realise that an hour probably isn't long enough to do this topic justice. If you talk about the peer operators, when a peer runs, it needs to have at least one private key that it is using to sign its own actions on the network. Yeah, so because it's an open network, basically everything that a peer does has to be signed, and other peers are going to check the signatures of each other in order to ensure that they're behaving correctly and that they've sent valid messages and that they're, you know, participating correctly in consensus. And most importantly, the convergent proof of stake algorithm, peers sign these data structures called orderings, which is kind of like their you know, proposed order of transactions on the network, which is what protects us against, you know, double spend and 50% attacks and all of these, and minor exacted value and all of these kind of attacks, is basically the way that the peers share these orderings. Every single ordering is signed, so nobody can fake an ordering which has been transmitted by another peer. But yes, so if you're a peer operator, they do need to have if you like, a hot private key for the peer itself to operate. Now there's and why do we care? Well, we care because peer operators have to have very high security if the overall network is going to have high security. If someone can come and hack all of the different peers, then they can do all kinds of bad things. Yeah. So we want the peers to have good security, and we want them to have a very strong incentive to have good security. And that means that they've got to be reasonably confident that they can run a server with a private key and secure that server sufficiently that they're not worried about anyone hacking it. Yeah. And that's it's not an impossible bar, but it's a reasonable bar. Yeah. You know, you either need to know what you need to know what you're doing roughly in terms of running a server. I mean, Linux servers are pretty secure out of the box by default, but if you do something wrong, you can certainly have a potentially compromised machine. So you do have to have control on that, and obviously you can do things like firewalls and, you know, which ports do you want to allow. Now, good news is Convex is very, very simple in terms of what it needs to run a peer. Yeah. There's no extra services required. You just have to have one port open. Yeah, and that port is going to the Convex peer server, and the peer server runs inside its own virtual machine, which has memory protection. So you can't have things like buffer overflows. You can't have attacks like that. And it validates every single incoming message. You know, it's got a lot of protection on the incoming info, but basically you can't cause a buffer overrun. You can't cause a lot of these sort of attacks that are, you know, generally what enables servers to get hacked. So it's got this very, very small attack window, if you like, into a peer. So we've tried to make it as sort of secure by default as possible. Let me actually just run one, actually, since we've got this here. So I had this set up to run a peer. If I do convex key list, I've got a bunch of keys, so I see I have a peer that starts with CCC, that'll do. So I'm just going to do a convex local start, and I'm going to do, I think it's public key CCC, key store password. Okay, so I think I've just launched 4 peers. Yeah, I think by default I'd set up to launch 4 peers. You can see one of the peers has this address CCC, which is the one that I specified, and because it's just a local network, it's created 3 other peers for me, just to, you know, so we've got a few peers to test. But that's the one that I sort of specified. I want that one, and it's sitting on port 18888, which is the sort of standard convex peer address, and these ones are sort of sitting on random ports. And then if I want to like actually use that account, I believe convex query, I do minus account 12. So I'm, oops, danger of live coding that. So I'm going to query minus account 12, and I'm just going to double check that account 12 has this key. And what's the, basically I'm asking what is the key of account 12. So basically it's query, so I'm just asking a question. I'm saying my account that I want to use is 12, which I believe is the account that the first peer starts with, and key is the code I want to run just to get the key that account is using. And yeah, so that account has the CCC key used. And now if I want to do a transaction, I can do account 12 again, and let's say I want to do let's say I'll just do some mathematics or something like that, which is a bit pointless to do in a transaction, but just a demo. Enter my password. Okay, and that's complete. Yeah, so it's now giving me back my result, which is, you know, 240,000. So that was running a transaction through the network using that key on a peer that I just started, and I'm just running that has that it actually has that same key. So, you know, if I was doing this properly, I'd create a bunch of new accounts and send transactions for my user accounts rather than the sort of the peer management account. But you know, it still works. So that's just a quick demo of how you can start a peer and how you can then use that same key to execute transactions. So if I was managing that peer, I would be using this account and, you know, putting any instructions I want in here to operate that peer. So, you know, changing stake or you know, whatever the operations I want to do with that peer. So yeah, just quick demo of sort of how that works. But in this peer that's running here, then you'll find that has to have that key effectively loaded in memory all the time in order for that peer to be operational. So yeah, you can't really use a hardware wallet for that. So the way I would think about it is you should have a dedicated server, it should be properly secured, it should be using a secure Linux installation, and it should only have that single port open, yeah, or open to the world, so that people aren't going to be able to attack some other port or some other service. You know, you've got some dodgy utility service running that opens up a port. That's a no-no. Yeah, you don't want to have any sort of gaping holes in your security like that, or potential security flaws. And it's pretty robust, and we've not had any plausible way of hacking a peer through that port demonstrated yet. So you know, but please try. Yeah, there's Convex coins bounties for anyone who can show a way of attacking port 1888 and taking control of a peer. Is like, you know, that's like a gold mine attack. So if anyone fancies having a crack at, you know, proving me wrong, then please have a go. So how a peer is secured against attacks? Yeah, I mean, I think I've sort of covered that. You've got a secure server. The peer keeps its private key private, and you don't open up any loopholes or ports that could get in. I would say that the peer does not actually store the key anywhere on its disk. Yeah. So if you shut down the machine, and someone stole the disk drive, they shouldn't be able to get the key, even if they, whipped it out of the server, because it will be stored in an encrypted format in the key store. So it's, it's decent. They'd have to actually be able to hack the live running instance in order to get at it reliably. Not directly network security. Is publishing peer reviewed papers a goal? Yeah. So we would love to publish peer reviewed papers. So if anyone is an academic or wants to review some of this, then very welcome to do so. I would say publishing papers is not directly a goal, but if people want to, I think securing the network is a goal. Yeah. So if creating good peer-reviewed papers helps, then yes. I mean, we do have a white paper. I mean, various folks have reviewed that from many different angles, and no one's found any gaping flaws yet. But I'm certainly welcome to academic collaboration. I mean, I see the value in good working secure software rather than having published papers. But if going through some peer review helps us to do that, then I'm all for it. Other question: is it possible to restrict the key of the peer, like no key rotation and a spending limit, and have a controller that is secure with a hardware wallet? Yes. Yeah. So what you can do, you can have the peer running with one key, but the account that actually controls the peer from a management perspective can have a different key, and you could have that secured with a hardware wallet. So yes, that is possible. Peers can't actually rotate keys, by the way. So although peer addresses are actually their public keys. So if you want to change the public key of a peer, what you're really doing is you're deleting that peer and starting a new one. Yeah. So there's not really such thing as key rotation for a peer. And in fact, probably the best practice would be to only ever create the peer key on the machine while you're using it, and then if you decide you want to go to a different machine, shut down the peer, delete the peer, and then start up a new one. Yeah. So you would actually have a controller account that is actually doing the sort of management operations and staking and controlling the treasury or stuff. So yeah, that's a good suggestion actually. I do like that, and it is possible because the peer controllers have a separate account if you want to do that. Awesome. Well, yeah, pretty much coming to the end. Hopefully, I've covered most of the things that are of interest to people, and shown a bit about some of the things that we do here. All of this is going to be live in Protonets, and there's development versions that people are very welcome to play with now and try out. Still tweaking a bit of the user interface. How do we make this easy, and also how do we make it idiot proof? Yeah, because I mean, I always do stupid things, so I want to make sure that it tells me if I'm doing something stupid, and ideally stops me, or at least says, are you sure? So some of this kind of security ergonomics, I think, is really important, and that's definitely critical. What security do I worry about? I would say the top worry to me would be peer security. Yeah, because I think users it's the systematic risk. Yeah, so users, yes, you could lose your wallet, you could lose some funds, but it's not systematic. It doesn't affect anyone except the person who loses their keys, really. And there are good options available for people who want to do it properly and who want to keep backups and keep offline systems and hardware wallets if they have significant assets that they want to protect. and that's got to be user choice. Yeah, individuals are responsible for their own key security, and I worry about peer security because if a large number of peers are affected, then they can take down the whole network, or they can do bad things on the whole network, and that would be a systematic problem rather than simply for someone making a mistake and doing something that might be bad for them, but doesn't really negatively affect the rest of the system. So yeah, so peer security I'd say is the top one. So the security of the peer servers themselves and the security of the keys that the peers are using is critical. Having said that, we do still have recovery mechanisms if the network was to be completely compromised, then at least they still can't forge a user's signatures. Yeah. So even if you hijack multiple peers, you might be able to temporarily crash the network, and you might be able to steal some stake from those peers, and they would certainly cause a major mess. But you still wouldn't be able to run transactions for user accounts. Yeah, because if you haven't got the user's keys, the peers can't take funds from people's wallets or anything like that. So yes, you would have to be of some drastic action to restore the network and restabilize and ensure that the peers are secured again. But at least user accounts and funds and balances could be maintained and restored if that happens. So even the worst case is potentially recoverable. Okay, well, fantastic. Thank you for all the great questions. Super exciting topic. I'm always learning new things about security and better ways of doing things. So please do continue the discussion on the Discord if anyone wants to drop by, and see you all again soon. Thanks very much, and have a great one. Take care.